Hello and welcome to this film, which is all about the ideal gas equation, and this is an equation which is based on the gas laws that we looked at in the last film. If you haven't watched that film yet, I suggest you do before you watch this one, because this one will make more sense. Hopefully by the end of this film you'll also understand what we mean by the molar volume of any gas, what standard temperature and pressure have got to do with anything, and we'll be able to use the molar volume of a gas to convert moles into volumes and vice versa. Okay, well, let's have a look at what the ideal gas law tells us in principle. Remember, ideal gases are those in which we've assumed that the particles take up no space whatsoever, that they don't interact with each other whatsoever, and not only that, but they collide with things with perfect elasticity. Now, all these things are physically impossible, okay, but they're assumptions which work quite well for us and allow us to use these laws for what we would consider normal conditions, so not extremely high pressures and not extremely low temperatures. But we might remember, hopefully, that the gas laws said that the volume is proportional to the temperature. That was Charles's law. The volume of a gas is also proportional to the number of moles of that gas, and the volume is also proportional to 1 over P. So we had Charles's and Avogadro's and Boyle's law. Okay? And if we say that the volume is proportional to these things, then this is like saying that the volume is proportional to the number of moles times the temperature divided by the pressure. And we might remember that if something is proportional to another thing, then that is like saying that the volume is equal to a constant times the number of moles times the temperature and divided by the pressure. Now, if we express our volume in dm cubed and our pressure in kilopascals, what we find is that the value of K is 8.31. And we give K a slightly different symbol. We don't call it K, we call it the gas constant, which is capital R. And in that case, if you end up putting capital R into this expression and rearranging it slightly, then you see the ideal gas law in its most common form, which is that P multiplied by V is equal to the number of moles times the gas constant times the absolute temperature in Kelvin. Okay, so there's an important law to remember. Let's see how we might be able to use it. Okay, so this is now assuming that the number of moles does not change. So I've got a set amount of a gas. Okay, if that's the case, then PV, as we know, is equal to nRT. And if n is a constant, because the number of moles is not changing, and the R is a constant, which we know, it's the gas constant, then n times R is a constant, and therefore PV is equal to a constant times T, and therefore PV over T is a constant value. So if I don't allow the number of moles of gas to change, then the pressure times the volume over the temperature is going to be constant. In other words, my original pressure, volume and temperature, P1 V1 over T1, is going to be equal to my new pressure multiplied by my new volume divided by my new temperature. Okay, now let's see how that works for us. Right, we've got this question here, 1.65 dm cubed of helium at standard temperature and pressure. Now before we go any further, let's just look at what that means. That is 0 degrees centigrade, but remember we're going to use an absolute temperature, so that's 273 Kelvin. And the pressure at standard temperature and pressure is 101 kilopascals. Okay, so plugging those values in and remembering that we're asked to find what pressure will it exert. So this is our new pressure, P2. Let's write an expression for what P2 is. P2 is going to be equal to P1 V1 over T1, divided by, because P2 was multiplied by V2 on T2, so divided by V2 on T2, which is the same as multiplying by T2 on V2. And if I plug my numbers into that, well, I've got an original pressure, P1 of 101, multiplied by the original volume, 1.65, multiplied by the new temperature, which is 323 Kelvin, remember, because it's got to be absolute. And that's all going to be divided by the new volume, which is 1.25, and multiplied by the original temperature, which is 273 Kelvin. Okay, and if I do the number crunching there on my calculator, then what I find is that my new pressure is 149.4 kilopascals, but I've only got two significant figures here, so my answer to two significant figures is going to be 150 kilopascals, or rather 1.5 times 10 to the 2 kilopascals if I'm really going to be strict about my significant figures. Okay, so that's how we use the ideal gas law, right? Now we'll move on and look at what we mean by the molar volume of any gas. Now the name kind of gives us a clue. This is the volume occupied by 1 mole of a gas. So if we know the temperature, pressure and number of moles, remember this is 1 mole of a gas and we're doing it at standard temperature and pressure, we know the temperature and the pressure, then we know from our ideal gas law that PV equals nRT. And in that case, we've got 101 to put in our pressure, multiplied by the volume, which is going to be our molar volume. This is the volume of 1 mole. Okay, and we're going to give that the symbol V subscript M. This equals 1, because we've got 1 mole, times the gas constant, 8.31, times the temperature, which is 273. And what you'll find if you do the sum here to find the molar volume at 8.31 times 273 divided by 101, is you find that at standard temperature and pressure, the molar volume of 1 mole of, so this is the volume of 1 mole of any gas, is 22.4 dm cubed. Okay? Now if I said to you, what is the volume of 2 moles of gas, you'd double that. So you'd be finding the volume for me. I'd be telling you the number of moles, N, and you'd be multiplying it by the molar volume, 22.4. So you're taking N and multiplying by the molar volume. And as soon as you've done that, you could construct a triangle for yourself, right? And then if you're asked the volume, you can always multiply the number of moles by the molar volume, so long as you're at standard temperature and pressure. Okay? You might, if you're not at standard temperature and pressure, you might just rearrange this to find V. Okay? But you could also use this triangle to find the number of moles. So if I'm told the volume, the number of moles is equal to the volume I'm told divided by the molar volume at that particular temperature and pressure, which will often be standard temperature and pressure, in which case we can use this figure here, 22.4 dm cubed. That is the number of dm cubed that each mole of any gas occupies at standard temperature and pressure. Okay, and it's called the molar volume. Now I would suggest that you practice a few calculations using that, and we're going to start looking at some gas stoichiometry in the films that are coming up now. But hopefully you now know what the ideal gas equation is, and you can use it to do some simple problems. You know also what the molar volume of a gas is, you know what standard temperature and pressure are, and you can convert volumes into moles and vice versa. If you've got any questions about that once you've done a bit of practice, or before you've done a bit of practice, please feel free to come and ask me straight away, and post a comment on YouTube.